Good morning, ladies and gentlemen. Welcome to the Introduction to Grid Modeling session. If that's what you're here for, you're definitely in the right place. And we are going to be beginning on time. So thanks to those of you who are early. Give us another 2 minutes and we will begin promptly at 10 o'clock Atlantic Standard Time. So thank you for joining us, and we will begin in a couple of minutes. All right, good morning again, and thank you so very much for joining us for the introduction to grid modeling capacity building session, or I should say good morning and good afternoon, because we do have some colleagues presenting from Europe. I am Sherry Farquharson, Knowledge Management and Capacity Development Expert for the Caribbean Center for Renewable Energy and Energy Efficiency, CCRE. And as a part of our mandate, the CCRE is currently undertaking several integrated resource and resilience plans across the region. So welcome to this capacity building series, which is complementing the integrated resource and resilience planning. And this is brought to you in partnership with the Technical Assistance Program for Sustainable Energy in the Caribbean, TAPSEC, which is funded by the German Corporation for International Cooperation, GIZ, and the German government in partnership with the European Union. We recognize that planning for the future of electricity sector requires an appreciation of the technical issues arising from grid expansion with renewable energy integration, as well as responding to demand side changes. And so these series of sessions are geared towards ensuring that the stakeholders in the industry understand and can adequately respond to these changes. Today, we delve more into grid modeling. We invite your participation throughout the session by typing your questions in the Q&A section throughout the session, and we will periodically pause to address your questions. So as the questions come to you, just type them there and we will address them throughout the session this morning. We have presentations from the UWI St. Augustine campus, as well as from Energy Nautics. Our first presenters, Professor Chandraban Sharma, Professor of Electrical Engineering, and Dr. Sanjay Bahadur Singh. And so we will begin with Prof. Sharma and then Dr. Bahadur Singh. I invite you to listen, share your questions, your comments, and let's have a wonderful morning. Prof. Sharma?
Thank you very much, Sherry. And thanks for the availability for us to be delivering this introductory course to the participant. And I want to emphasize it's introductory, and the number of topics we have to cover in this introductory is about 6 or 7 topics, and therefore we will be going through them a little fast, but we want to whet your appetite because for details, the 90 minutes we are given will cover one topic only if we need to go into details. So let's start the ball rolling. These are the two persons who are going to present today. So I am Chandravan Sharma, and the next person who's going to present in the about 45 minutes from now will be Dr. Sanjay Bahadur Singh. So what we are expecting here from this particular presentation is an appreciation of grid modeling fundamentals, for you to appreciate the requirements to build a power system model in software, appreciate steady state studies, which would include power flow and short circuit analysis, as well as transient analysis. And we have it in the order that you normally would do it: power flow, short circuit, then transient, because that's how you build the model. And finally, to identify the data requirements for accurate modeling and analysis. One of the things that has to be stressed here is that your model and the outputs of your model depends on how accurate your model is and the data that you have. So it's just like bad data in, bad output. So the issue always is your model, how you can derive your model and how accurate the data you have for your model. So let's look at some of the basics very quickly. Every power system has three major components: a generation section, which is the source of your power. Ideally, we are looking for the source being a specified frequency and voltage. The system, the transmission system that carries the power throughout the network, that's like your highway, your power highway. So ideally, you're assuming that it's perfect conductors you have, perfect meaning lossless, and then load, which is what you're sending the power for, which are your consumers, right? Which would be your industrial, your commercial, your residential, your government agencies. So these are the three components you'll be looking at in terms of modeling. So why do you model? What we have here is an extract from a Power World slide where we have a power system. It's producing power, and we have two simple generating stations, one here and one here, where we are looking at the power flow, and these circles tell you, depending on how much blue is there in the circle, it tells you how loaded the line is. Just remember, each line can carry a fixed value in terms of power flow, and you want to make sure you don't overload the lines, else you'll get severe voltage problems. So this is a stable power system, as you can see there, in that we have the power flows. You have a matching of power generated and power consumed. What we need to do now is to simulate this real-time system into an actual software model where we can get the operation and we can decide and explain what may happen if things were to go wrong. Why we want to do it? Because it's cheaper to do it in a model than to try to do things online, because it's very costly, and if you make an error on real life, you not only will cause damage to equipment, but you can actually kill people. So in terms of my power system analysis, we want to ensure that our practical power system is safe, reliable, and economical. In our modeling system, we are trying to encompass several aspects. One would be planning and expansion. What are we going to do if we need more power in the system, if the power system is growing? How I operate the power system to make sure I have economical operational power system. And the types of analyses that I would need to do would be transmission line performance, power flow, contingency analysis, economic generation scheduling, fault analysis, transient studies, and all of these, which would be these 6 areas, they all require component modeling of the system, meaning that a method whereby I can emulate what is happening in real life in the software domain. So as I go forward to that, this is what we're looking at. This is our power system model that we require. And from the model, we have all these limitations that we have feeding into the model, software, accurate, complete data, contextual knowledge. Contextual knowledge has to do with what is really happening in the system, what you want to do from a real operation, tools and techniques. And one of the areas that a lot of people neglect is interpretation of the results. Just remember, the software model is just that. It's a model. Many a times failure occurs in understanding what the output of the model is saying. The model is not an AI technique. The model gives you a result depending on what you have put into it. Someone has to interpret it. And usually the person who interprets it is a person who has some actual experience. And that's the person who can really interpret what is really happening. I can give a result from a model to two different persons, one who has just come into the system and one who has been there for a long time. And you can get two different interpretations typically. So it's very important for interpretation of the results. So what you need to do is to develop a lot of planning in terms of software familiarity. And you want to ensure that I have all the data that I require to ensure that I feed into the model that I have. I want also to ensure that I have actual live data, which I can use from my data analysis and data capture, and reduce my costs in terms of who I'm going to pay for doing these things. Now let's look at a simple power system here. And we're going to look, this system is very nicely flowing. It is balanced. It is what you will talk, when we come into power flow, we'll talk about it as converged. And everything is flowing nice and honky-dory, as we would say. By the lines we're seeing here, power is being generated from the generating station. So we have 5 generating stations, and the green line tells me power flow is okay. Now, what happens? One of the line goes overloaded. So I just have one line goes overloaded. And in terms of that, this line, because it's overloaded, my protection system removes this line, because I cannot continue to carry the power along this line because the current is too high, the conductors are getting too hot, and my voltage drop is also getting very high. And my protection system is so designed that I open this line, so I've lost this line. Losing this line also causes another problem. It causes a redistribution of the power flow. And what happens with the redistribution of the power flow? This line here, which before was, if you remember, it was being overloaded. So this line now becomes overloaded, and I've lost this line too, for the same reason as this line, because power now starts to redistribute along the power system. Because of that has happened, I have more problems in the system. I lose more lines, and it continues to lose more lines. More power is being taken from these generators here to take up the slack. I get an under frequency, over frequency problem because I've removed this here. I've removed this line. This generator continues to generate, but there is no way to put the power. So in the instantaneous mode, this goes to over frequency and I trip. And what I have right now is a complete blackout in terms of my power system. And that blackout has to do with the fact that probably I did not do a contingency analysis of my power system, as well as I did not, after doing that, did not do a proper protection coordination study. So all these are required in terms of doing my proper power system analyses. So the moral of the story, as we have it here, is the initial generation dispatch should always be checked and modified to avoid any overload following the loss of any component, as well as once I've done that, I have to also check my protection system. And one of the errors that many people make in a power system analysis is that we forget that once my power system changes, if I add a line, if I remove a line, if a line goes into maintenance, my protection system also should be checked to make sure I do not compromise the security that I had on my system. So we need to do that almost on a regular basis to ensure my system is properly coordinated and properly protected. So that's the initial salvo that I have on this particular system. If there are no questions, I'll move on to circuit analysis, which would be one of the major areas we need to cover in our power system analysis. So in circuit analysis, we are looking at the phasor representation of the power. And what we're trying to do here, we have our voltage and we have our current. And what we are showing here in time is that there is a phase lag between the voltage and the current, which is phi. And we can now represent this time domain system into a frequency domain system by a transformation. And this particular area is where we go into what is called phasor modeling. And we would actually do a lot of these in our power system, and that we will forget that the actual generation is a sinusoidal, and we are going to lump all that in just a magnitude of the voltage and the current and the phase relationship between the voltage and the current. The reason we are doing that and why we can do that basically has to do with the fact that once the generators are generated, my frequency is going to be stuck between very close numbers, and therefore I can really assume that whatever I get on the output would be at the same frequency unless I get into transient analysis. Then I have frequency deviations. So the area that is that the voltage is root through V. V here is the maximum value, the peak value. Root 2 V gives me my RMS value. So this is represented as the voltage vector, which is V angle 0. So we are referencing all our measurements with reference to my voltage. And if I reference everything with respect to my voltage, my current is lagging by phi. And so I represent the current vector as I angle phi. My power definitions. The real power is the usable power. That's the power that actually does work and depends strongly on the power factor in terms of its equation. And it's in terms of watts or kilowatts or megawatts, reactive power. That's the requirement I have, which is inherent in any AC system, which has to do with the electromagnetic and electrostatic charging and discharging of the inductors and capacitors on the power system. So P and Q, these are what we have. The Q, we cannot get rid of the Q. Q is an inherent property of all AC systems. However, the only power that actually does work is P. This is some of the equations that will come up in terms of my power system, where we have here, I have a three-phase generator supplying a three-phase load, and I have the equations for the three-phase generator, the three-phase load, where I have the angular displacement, and that's between the current. So if the current in the A phase is phi, minus phi, the current in the B phase will be minus 180 degrees from, away from that. And the C phase again will be minus 270 degrees away from that. That's the inherent vector orientation of the three-phase system that we have here that is being presented to the load. Because the system is balanced, and balance means that the magnitude, the RMS value of the current in each phase is the same, and the vector relationship between each other is 120 degrees and constant, then I can reduce this three-phase load to a single-phase equivalent load. And whatever is happening on this single-phase equivalent load, I can say it is happening on all the three phases, save and except it's displaced from each other by 120 degrees apart. So that's a general statement you're going to use for your power system. The assumption there is that my load is balanced, and balance means that the current in each phase is, from a magnitude point of view, the RMS values are all the same, the voltages are all the same, and the phasor relationship between the three phases are all 120 degrees apart. Now, in a normal power system, we have several units that we need to look at. We have synchronous machine, we have transformers, we have overlap conductors and cables and transmission lines. We also know that all the systems are at different voltages. So you have a power system, you start at the generating station, it may start at 12 kV, 13.5 kV, and then you step it up to the transmission voltages, but maybe one step, two step, might go from 33 to 132, back down to 66, and probably for distribution to 12 kV or 13 kV and down to my general utilization of 220, 110, 120. Because of this varied voltage system or the power system, I need a methodology to handle it, and we come to what is called the per unit system, where I am referring to all my systems on my power system, on my general power system network in terms of a basis or a reference. So that's my per unit system. I am normalizing everything onto it. So what the per unit system does, it removes a lot of the problems, let's say for transformers. So I can remove this transformer network, okay, from a per unit system by just replacing the transformer in terms of an impedance. And what I've done with that is I now have converted this power system into an equivalent, and I'm going to use a word here, DC type of system, meaning, and I'm only using DC there so that you can understand that I can now start an analysis equivalent to, not equal, but equivalent to how you would do a DC calculation. It simplifies your calculation throughout my power system. The challenges that we meet up is in terms of my load. How do I model my load for my analysis? And remember, my loads on my power system will comprise lights, refrigerators, motors, furnaces, and these are going on and off. They also change in time, weather, depending on the area the people are living in terms of the income stream. We need to now find some general model for these type of load, which is called the load modeling. I need to represent this load characteristic in terms of bulk power delivery at a particular point, where I can put all of them together in terms of a kind of a model where I can say generally in this particular area of the country, the load can be represented by a fixed value for a period of time, and it moves from that because it's all averages out. And I have to know which loads I can put for a particular value, the P and Q value for the load, which means the power and the VARs in terms of what the load is taken. In terms of the other model is my synchronous machine. The synchronous machine here is my actual fossil fuel generator. And why I say fossil fuel is because when you get into wind system, your wind generator can be synchronous, but it can also be an induction machine. But most of your generators that you have on your system now would be synchronous machines. And we need to model the synchronous machines in terms of the synchronous impedance, the open circuit voltage, the EMF, the voltage delivered at the terminals, the internal reactances. This here represents the actual synchronous machine with the three phases A, B, and C displaced 120 degrees apart. And this is your rotor, which is actually providing the field for my system to generate my power. And the rotor is what is being driven by the turbine or the motor or the generator that the machine that you have that is turning this turbine. And actually this turbine with the machine that you have is turning it would be what we will call, and you'll see it in the future, part of what is called the inertia of your system, of this particular synchronous generator. So one of the assumption we make in a stable system, and it's not an assumption, it's true because they all pull in together, is that each generator operates with the same electrical speed, which will resolve into a same mechanical speed, which gives you the frequency, and the proper interconnection of the rotating machine with the network is what is called synchronization. Synchronization is making sure that all the generators on the power system are operating at the same synchronous speed, same electrical speed, basically, and you're producing the same voltage magnitude that you're looking at. The angular displacement would be different depending on who is generating, which generator is generating more power or not. But that's for the future. The other model that I have to do is for my transformer. This is a typical transformer electrical model where I can see the secondary of the transformer, which has a resistance and an inductance. This is the ideal transformation, which is what is giving me my turns ratio, which is 2000, which is 2 to 1 or whatever the turns ratio is. So this we call this an ideal transformation, meaning that whatever voltage I put in here, it's going to come out at this value here, but multiplied by the ratio of N1 and N2. This is the primary side of the transformer, which is my input voltage, where I have my leakage here, which would include my hysteresis loss, my eddy current losses, magnetizing losses in the core, and this here represents the model for the impedance and the resistance of the primary. Now we want to remove this transformation, ideal transformation ratio, and the way to do that is that we would refer all the secondary impedances to the primary in terms of its ratio. And that's an operation that occurs actually once you do the per unit system, you have converted the system per unit. Inherent in that conversion, this occurs. The other aspect we have in terms of our modeling is overhead conductors. Overhead conductors are comprised of several types. We have homogeneous conductors and we have non-homogeneous conductors. Homogeneous conductors are conductors whose individual strands are of the same material. The conductor properties, meaning the physical properties, the mechanical properties, the electrical properties, are all the same. And some homogeneous conductors you can refer to are things like all aluminum conductors, where everything here is aluminum and it's made from one homogeneous type of material. The non-homogeneous, as can be seen by the diagram, comprises an outer conductor, which is the aluminum, and steel that is in the inner core, which is really a reinforcement in terms of giving you your ability to tension these conductors. So these can also be conductors which are, well, aluminum and steel at the center, okay? The other type of conductors we have is our cables. And if you look at how the cables are constructed, the conductor is way in the center, but each one of the layers of the cable are what gives me my magnetizing loss on the conductor, as well as the coupling coefficient that I would have. So that's the modeling of the cables and the modeling of the naked conductors are completely different. And we have to understand how these are modeled. The other model that we have to look at is our transmission tower design. If you notice, we have shown on this structure here, we have 12 different designs. And each design, depending on where let's look at one of these here, this B1 structure. The coupling between each phase is completely different to the coupling between each phase here. And therefore, by extension, although I may use the same conductors on both structure, let's say the B1 and the B2 structure, the actual impedance as seen by the network by these two different structures are going to be different because the magnetic coupling between the phases are going to be different. So in part of getting the cable's impedance for doing your analysis, I must also know what is the tower structure, because that's how the conductor are stranded across your system. So that's where my impedances are going to change for the same type of conductor. Resistance, this is where my losses actually come into play, and my technical losses are basically due to the resistance of the system. I have my DC resistance, which most people are very familiar with, And then I have my AC resistance, which has to do with skin effect and my operation, whether I'm at 60 or 50 hertz. And we know that the DC resistance is given by rho L on A, where rho is the conductivity, the resistivity, sorry, of the conductor. And the AC resistance is given approximately by 1.02 plus the DC resistance. But depending on the manufacturer, you'll get this from the manufacturer, basically. Bundling conductors, where I bundle conductors basically so I can carry more power on my lines. So I put them together. And in terms of getting the actual impedance of this bundle conductor, I have to get two aspects. I also have to get what is called the geometric mean radius and geometric mean distance. The geometric mean radius is really what is the equivalent radius of all these conductors which are in this bundle. What is the equivalent radius? And the geometric mean distance is really what is, we assume now, I haven't gotten this now becomes an equivalent conductor, and this is an equivalent conductor, and it's now the distance as you strand it on the tower that we have shown before, what is the actual geometric mean distance between these two conductors. And that is what is going to give me the actual impedance of the line as seen by my power system network. So therefore you need to get those data done properly, or else you're going to get wrong values in terms of my analysis. So one has to be very careful in terms of how I do this. You cannot neglect how your conductors are laid in the ground as well as overhead, because each formation you use is going to cause a variation of the impedance of the line. We have our transmission line parameters. Okay, we have our RLC and conductance and resistance, inductance, capacitance, conductance. We can calculate it using hand equations, or we can calculate it using the equation within our software, depending on where you are really in your system, what type of software that you have. Each one can be calculated once I know the values that I have just looked at before, and I can get the values that I need for my system. And those values become very important inputs into my programs. The models, I can have really three types of models, which would be the short, medium, and long line models. Because I'm assuming that most of you all are in the Caribbean, the long line models don't really hold much importance for us, but we need our short line and medium line model. The short line transmission model may be used when the line length is less than 80 kilometers. And it is basically given like this, where I have my resistance and my capacitance along the length, sorry, not capacitance, the inductance along the length of the conductor. This Vs represents my sending voltage, which is my input voltage, and VRB is the voltage at the end of the line. The length of the line is L kilometers, and the line series impedance is given by R plus JX. The total impedance of the line is given by ZL ohms in terms of the value of the line. In terms of my median line transmission, which is between 80 to 250, I now have to take into account the inherent capacitance between the conductors, and this capacitance is now represented by my admittance between the lump admittance between the sending end and the lump admittance at the receiving end of my particular line. And this is how we are going to get the actual line model, but this R and LX would have come before from whether my system is bundled, what is the formation, etc. Okay, so I'm going on to fault analysis now. Do we have any questions here?
Prof, I think you're doing an excellent job of laying the foundation. No questions have come in as yet.
Oh, well, it could be that they are stunned. Anyway, let's go on. Fault analysis. So let's look at the fault analysis. This is really what happens when a fault occurs on the system, And fault means that there's some connection between the live conductor to ground. The connection could be a zero resistance connection, it could be an impedance, it could be a high resistance, but there is a current going to ground. So in my fault analysis, we are looking at anything that disturbs the natural and normal flow of current. One of the short circuit analysis, short circuit that you get is lightning. Most of the time, a lightning hit the conductors, and you have interface short because of temporary ionization of the air between the conductors here, and they short out, or you get a tracking straight to ground. You can also have fault due to salt on the insulators, and we will have many of these depending how close my conductors are to the sea, and we all are prone for that because we are islands for most of us. Flashover, meaning that this is when wind is blowing. Maybe you get a small little storm and the line starts to swing and they touch each other, so that's when the lines are not tension and they're actually looping too much. You can also have the trees touching these. You have a conductor fall from a pole. They say one of these just fall to ground. You could have an object fall across the conductors, or a stick fall across here. Most of the times, what happens too is that if this is going through forested area, sometimes a snake fall across there. Sometimes a bird the wing of a bird, a hawk probably shorts it out. Okay, or cable insulation failure, which is the one you really don't want to happen because that causes for major changes. You can also have a fault which is called an open circuit fault, which is when at the joint here where I have the conductors meeting at this point here, you can have the loop here, which is a pigtail from here to here, and that burns out, and it becomes an open circuit. So that you see that as a fault also on the system because now I have an unbalanced system. I have a balanced system on this side, on this side, it becomes unbalanced. So that's a fault. The main effect is high currents in terms of heating and electromechanical stress and voltage levels. I can have over voltage, I can have sags, I can have under voltages, all of which can affect my equipment which are on the system. I have to do fault analysis so that I can now decide how to set my relays on my system. So my generators, my motors, my relays, which one should open if there's a fault occur here, which one should open. My switching schemes, if there's faults on the system, how do I divert the power to different areas? So this is what I require in terms of my fault. The analysis I'm looking at will give me my ability to do proper protection coordination of my system, selection of the breakers, meaning my short circuit ratings of my system, selection of the current transformers to make sure the current transformers I use do not go into saturation when a fault occurs, selection of the protective devices as well, contributions to generators and motors, depending on where my fault is or how big the motor is. The motor actually, for that period of time of the fault, will also contribute this motor here. If there's a fault somewhere here, depending on the size of the motor, for the few cycles that this area is under fault, this motor can contribute some current to the fault, and calculation of the grounding voltage potential rise. To do these analysis, because the system becomes unbalanced, I have to now utilize a mathematical technique to analyze this fault. And this mathematical technique is called the symmetrical components theory. It's a theory which was developed by C.L. Fortescue in 1918. Actually, it was developed by a Russian mathematician, Stovkis, in 1915. But is, of course, an electrical engineer who puts it into practice. And Fortescue showed that this methodology, where I can take three unbalanced systems and convert them into three equivalent balanced systems, such that the vector sum of these balanced systems now gives me what is actually happening on the unbalanced system. These three unbalanced systems are called the zero sequence system, the positive sequence system, and the negative system. And what would happen in my symmetrical fault analysis is I would analyze each one of these systems individually, find out what is happening on each one, vectorially sum them, and whatever the answer I get when I vectorially sum it, that tells me exactly what is happening on the faulted power system. Why I did this? Because if these systems are now balanced, mathematically balanced, remember, this is not a reality that is happening outside. Outside, the system is unbalanced. Mathematically, for I to understand what is going on, for you, the user, I am mathematically introducing a technique to convert an unbalanced system mathematically to a balanced system. Since it's balanced, since each one is balanced, all I need to do is to look at the single phase equivalent of each one, because I know for any balanced system, the single phase equivalent is going to give me the value of the voltages and currents on every phase just displaced by 120 degrees apart. So that's one of the major mathematical techniques that I need in terms of fault analysis. And in terms of my short circuit studies, I need to understand what are the positive sequence impedance, the negative sequence impedance, and zero sequence impedance. The zero sequence network only has zero sequence impedances and zero sequence voltages. The positive sequence network only has positive sequence impedances and positive sequence voltages. The negative sequence impedance network has only negative sequence voltages, negative sequence currents, and negative sequence impedances. They are all displaced except for the zero. The positive and the negative are displaced 120 degrees apart. However, the positive is rotating clockwise and the negative is rotating counterclockwise. The zero sequence is rotating clockwise, but they're all in phase with each other. Okay. So I need the impedances, positive, negative, and zero of all the system, all the equipment I have on the network, which were the generators, the transformers, and the lines, the transmission lines, for me to be able to solve a system like this. So the transformer sequence I need to ensure for a system like what I had before. Okay, let's look at this system. I have a generator. I have two transformers. I have, because it's a simple system, I have three line system. I have a line connecting 1 and 2, a line connecting bus 2 and 3, and a line connecting bus 1 and 3. So this is line 1 to 2, line 2 to 3, and line 1 to 3. I have two generators. I have the generators in terms of the connection. This generator is star connected, earthed to ground through a 0.3 inductor. The transformer is a star-star earthed transformer. This transformer is a star delta earthed transformer, and this generator is also earthed. Depending on how the earthing occurs on the system, your zero sequence network is going to change. So let's see how we can just put this into a networks. The zero sequence network, I have my generator. The thing to note here is that in my zero sequence and my negative sequence, there are no voltages generated, because we are going to assume that the only net voltages that are generated are positive sequence by the generators. Your generators only generate positive sequence values. So therefore, there are no generated EMFs in your zero sequence and in your negative sequence. The positive sequence and the negative sequence, in terms of how it's constructed, looks the same. The only difference that you would see would be you have a generated value, which is the EMF of the positive sequence network, but there's none in the negative. Anyway, the impedances are all the same once there's no rotating equipment on the system. The only impedance that you see going to change would be the impedances of motors and of course the generators. If we look at the zero sequence, however, the zero sequence depends on whether there is a path through Earth for the zero sequence currents to flow. So I have a path for the generator G1, T. It goes through this transformer because it is earthed on both sides, come through the transmission system, come to this transformer here. So it can go enter the transformer on the primary side, but it bounces up a delta connection and it cannot go beyond that. So the zero sequence only circulates here and is represented by in the network as a value or a line going straight to the reference node, which is the Earth in the zero sequence. And therefore, the zero sequence network, the generator 2, and let me just refer to it, this generator here in the zero sequence network does not come into play. What is to be noted too is that the impedance that we use for the generator is 3 times the impedances as we see on the system. So you see that we actually have the impedances would be 3 times that you have on our system. So that's basically how we do it, and that's how we set the network up into our design, into our software. I need to get all those values in the software. If I don't get those values, or if I get those values wrong, the answers that I'm going to get are going to be wrong. It's very important. So this is where we are right now. I've set the framework. The next section, we're going to look at power flow. Any questions that I have?
Yes, Prof. No, you do have a few questions.
Okay.
And as you were wrapping up, and you were mentioning the all the inputs that are going in that you need to ensure that you can accurately model the system. I'll just ask, with all of these different parameters, these different components of the grid that we're modeling, what adjustments need to be made in terms of resolving the model with the actual grid?
Well, the only way you'll know if you have a problem is, let's assume you have done your analysis, okay? And you have values. I'm going to assume you have values for each one of the components. And then I do a load flow. And my load flow has converged. And when it has converged, I am seeing values on the load flow, which are not the real values that I have outside. That immediately tells me that something is wrong in the model. And you now have to go back and try to pinpoint where these errors are coming up from. Now, if you have good voltage measuring equipment and current measuring equipment on your system, you can now go back and have a snapshot of what the values are and see where you are getting your differences. And where you're getting your differences could now target where the problem is. Could be a generation problem. It could be that your models for your generators in terms of its impedances are all wrong. Or it could be that your lines, the models you have for your lines are wrong. It could be you had a right model and the lines were changed sometime and someone changed the structure and it has not been recorded anyway and no one has actually redone the structure to tell you what the actual impedance of the line is now, and therefore it's completely wrong. So you have to work back on that until you get it correct, until it converges. But it's an iterative process because you have, that's where the knowledge base comes in, where someone who has experience. The person with experience is the one who now comes back to you. And in our case, many people call that person with experience the consultant. Comes back with you and helps you to find out where the errors are in your model. Invariably, what people would do, what system managers would do is that initially, if they don't have the experience, they will call in a good consultant and who would initially set up a network for them. And then it is your job to maintain that network. That's where the problem many times lies, is the maintenance of the network, because once we get it working, many of us, because other pressures take on the job, we forget about maintaining it. and we assume it's going to be static. And that's what you need to do all the time. I hope that
All
answers it.
right.
Oh,
Yes, it does. Thanks, Prof. And we hope that after we've gone through a few iterations of this IRRP capacity building, that we won't be calling in as many consultants as we
exactly.
do now. All right. So next question. What are the minimum data requirements that are needed to model the power grid to a reasonable representation?
The minimum. Well, I've showed you the minimum there. You need the problem in terms of modeling the grid isn't as difficult as doing transient analysis. The transient analysis one is the difficult one. In terms of getting your short circuit analysis and your load flow, it isn't as difficult as transient. So in transient, you can get a lot of the information, the generators information you get from your vendors. They're going to supply that for you. The transformer, you get it from your vendor. It's on the nameplate actually. And the lines, it depends on your line formation. You can actually work that. If you can't work it, you'll get a consultant. Those are the minimum, the R and L parameters that you need. When you get into transient analysis, that's where your issues come in terms of time constants. And my colleague is going to handle some of that. Right? But that's the difficulty. The transient analysis is your difficult. Not that the other modeling is not difficult to do, but in terms of degree of complexity, the transient is very complex.
Okay, final one for you before we allow Sanjay to step in. With respect to models, should more than one model be maintained? That is a planning model and a separate operational model.
An operation model is only one that you utilize if you're doing it online and live. So if you're not doing any analysis on live, meanwhile the system is actually running, right? You want to get an answer very quick. That's the only time both models are different, because one of them you want to converge very quickly. But if you're not doing it live, then it's the same model you're using.
Okay, all right. Thanks, Prof. We are gonna allow you to hand over to Sanjay now. I see there's another question here. We'll take that question we have a couple of other questions we'll take in the next break. And so our next presenter, Dr. Sanjay Bahadur Singh, also from the Faculty of Engineering at UWI St. Augustine, and he will take us through the second half of our framework for the introduction to grid modeling before we start looking at the software. Sanjay?
Thank you, Sherry, and hello, everyone. And thank you to Professor Sharma for laying the foundation for me to continue. What is very timely about the discussions there were with respect to the elements of the power flow, which I think puts us on the right path to ensure that what we're going to discuss gives you a better appreciation of how you go about this. So when we look at the power flow, what is a power flow and why do we need to have a power flow? Essentially, what we really want to do is observe the flows on the network. What we discussed earlier would have been an introduction to your real and reactive flows. You identify that you have different components on your network, transmission lines, generators, you also had transformers. And what we want to identify would be the impact of contingency, the impact of configuration changes, the impact of an outage. What would be the equivalent voltage magnitude and angle at the particular buses? Essentially, how can you identify that your quality of service that you are actually receiving is what you have the utility has been supplying to you? And most of all, another key point here is to identify how you can manipulate that. So from a design perspective, you would want to ensure that you have optimal operation and distribution of your loads, and you can get a snapshot of that. And that's the most important bit, because it can help you define your operational guidelines. So when we talk about snapshot is critical. You go to the doctor for a health checkup. Essentially, what a snapshot gives you at the doctor will be how well is your body working. You take different diagnostic tests, and it gives you some measure of indication of what the performance is. And the power flow is no different to a power system. It is going to give you a snapshot of the present operation of the system at this point in time. Now, this is a steady state picture. In other words, this is how it operates at this point in time because you have no changes. It is constantly operating in that mode, and that is very critical for you to appreciate. And how do you define that? Essentially, you will have buses and branches that will give you a series of equations. You will see voltages, you will see angles, you will see values of real power, values of reactive power, and all these are the equivalent symptoms that you are going to look at, and you want all of them to be within a particular range that is governed by the limitations of your network, and that will ultimately identify if at this point your power system is operating in a healthy position. And of course, the key thing to note is with all your equations, the one fundamental law here is that your generation must balance your load, and we often say plus your losses, because no power system is going to be ideal. So you must have some energy balance. So when we talk about this power flow problem, it is not a simple problem. It is very much non-linear. And when things are non-linear, they tend to get a little more challenging for us to deal with and require some mathematical tools and techniques. We may be only able to identify a simple solution for a simple problem, and that may be a two-bus system. However, many power systems are not two-bus systems. And when you look at this snapshot here that was showed earlier, what you are essentially identifying would be not only the flows on your transmission lines, but you're also seeing that you have some measure of control over the generators. You are identifying the directions. And what we are going to discuss a little more is how do we actually go about and achieve that? Also, how does it actually happen in the software? One part of using software is understanding how software operates. And if we look at the snapshot at that point in time for a simulation, you'll be able to identify, if the power changes, how does that link with the angle? And therefore, we will be able to identify that there's a direct correlation. Similarly, for a change in reactive power and voltage, there's an inverse relationship. So we would want to identify not only these characteristic features for when we look at the results, but it also gives us an appreciation of our real flow, whether my sending end angle is greater than my receiving end. I will be able to get the direction of where flow power is actually flowing. Just like at your homes, when you have water, you have a pressure difference, it creates that path for the water to flow. It's very, very similar. And then, of course, you have a similar relationship for your reactive power flow, where the magnitude of the sending end must be greater than the magnitude of the receiving end. So once again, knowing that that picture you're taking gives you real power, reactive power, voltage, and angle, what you essentially have will be not only the numbers, but a potential appreciation of how these numbers are actually allowing the flow of power, real and reactive, from one part of the network to another part of the network. And that will also help us identify if we have any overloads, if we are actually operating within our limits, and how we can improve the performance of our network. One critical bit is how do we model this power system? And it gets a little bit complicated, but I must introduce you all to this concept of the bus types. We have different types of buses in our power flow. We may be accustomed to, we have a generation station located at X, a generation station located at Y. We have a substation at this particular point that we pass every day on our way to work, so wherever we may go for, whatever we need to do. But more importantly, from a modeling perspective, each has a classification. We can have a load bus, a voltage control bus, and what is known as a slack bus. And these three classifications help us identify how we can formulate the power flow problem. But like anything else, there's no one set way to solve a problem. What I'm going to introduce you all to would be at least here 5 potential mathematical solutions that help us solve this power flow problem. The Gauss-Seidel, which is one form, and then you have the other 4 forms, which are all linked to the Newton-Raphson. So essentially, we have 2 broad categories that we are going to discuss here, and then we will dive a little bit, can't go too deep into this based on time and the mathematics behind it, but it will give you an appreciation of when you click on that solve button, you will see these options come up, and you must be aware of what that means in terms of the time for computation and the accuracy of your computation. So the Gauss Seidel, well, to be fair, it is the simplest iterative method. And if we look at this graph here, what you see is this oscillation about points along the curve until you get to that point of convergence. But it all starts with the assumption of an operating point. And you must start with that operating point, for which you plug this into a formula and then you find your convergence. The Newton-Raphson. The Newton-Raphson is based on the Taylor series expansion. Now, the beauty about the Taylor series expansion is that we utilize the derivative, and the derivative, which is essentially where the power lies for the convergence, gives us a faster time. The power of this method is in the derivative, and unlike the Gauss-Seidel method, the Newton-Raphson method requires two functions evaluation at each iteration. The convergence property is a lot better than the Gauss-Seidel. Why do we need this? Well, guess what? These mathematical tools must be translated to a practical approach. So now that we have discussed earlier that when you go to the doctor and you get these values of these tests that you do, and you look at your symptoms, and for a power system, it will be power, real power, reactive power, voltage and angle. We must now apply this to a mathematical tool, and that is the Newton-Raphson. If I were to take this example here, and it's very mathematically intense, but fortunately for us, we are not going to go into that today. We'll save that for another time. What we get here is the opportunity to identify that the change between real power, reactive power, voltage magnitude and voltage angle occurs for each bus in a system. Each bus in a system. So in this example, we have 3 buses. 3-bus system is a simple system, yet we have managed to have some interdependencies between 9 variables, and that is noted as the Jacobian matrix, which gives us a measure of the sensitivity of real power and angle, real power and voltage, reactive power and angle, reactive power on voltage. That is based on the bus types that I mentioned before. So what is critical here is that the Newton-Raphson tool, although complex, is very, very potent. It is very complex, but it gives us the best possible chance to get convergence in a fast time frame. Given that it's an iterative process, I'm just going to show you some snapshots. Don't want to get you all too intimidated by this, but these snapshots give us an appreciation of the matrix-like formulation of the problem, which is the Y bus for the admittances, Y for admittance. Admittance is the inverse of impedance, and if we go back to what Professor Sharma discussed, we have properties such as R, resistance, inductance, L, and capacitance, and those are all captured in the Y bus, for which we utilize either we could utilize your polar form, or if you wanted to translate that into another form, you can. We must work with radians. These equations that you see below are characteristic equations that you fortunately do not have to work by hand. However, what is critical is to identify that each equation is linked to the bus type, and therefore when you define your power system from that piece of paper, you must now correlate, this is my PV bus, this is my PQ bus, and this is going to be my slack bus. So contextually, you are going to recognize that that information now must be applied within the mathematical tool that you're going to employ to solve the power flow problem. And if you take this mathematics one step further, it continues to get exciting, but most importantly, you don't have to do it, but you need to understand what it is doing. And what it is doing, it is creating that iterative part based on the differential of the tangent at that point for the solution for convergence. Convergence will occur when successive iterations satisfy a very small tolerance. These are usually 10 to the minus 3, 10 to the minus 4. And this is an example of what the process looks like. Again, we are not going to go through the maths, but this actually happens in the background. So when you do a power flow, just think about the maths that happens in the background. And if you put in a value that gives potentially an erroneous value in your computation, what you're going to get out will not be any closer to the true value that you should get that reflects the operation outside. So the Newton-Raphson can be utilized to give you your real powers, your reactive powers, but it's not the only tool. It is the most complex tool, it is the most elaborate tool, and is the most accurate tool that you can use. And you will see that button in that power flow option. So what happens now when you don't have a power flow solution? Can this happen? And the answer is that, well, it does not always have to converge. So the question here is it possible for any set of power injections and voltage magnitudes to always yield a valid power flow solution? And the answer is no. Why? Because at the end of the day, your generation must balance your load plus your losses. That does not mean that mathematically you will get a solution. When you look for convergence, you are looking for the mathematical tools and techniques to be interpreted back to the real domain. You can have a position where you may not get a solution, or you may get a solution that is not practical. And that is key to interpret in your results. I want to move one step further and look at the decouple, fast decouple, and the DC. And essentially, what we have is when we want to apply the power flow, we would like to get an answer in a very reasonable time frame. The Newton-Raphson, while it is the most complex, is mostly computationally intensive tool that you can use. It is hungry for processing power. What you end up with is you run a simulation, and depending on the size of your network, depending on your size of the network, the calculations that you have to perform, you may end up waiting a little while. So the ways to improve on that would be, well, here's what you can improve your computational power by adding on more processors, adjust your computing requirements. But what you can also do is apply other methods, particularly if you want to run more iterations of a particular configuration, more simulations. So as you all were discussing earlier, where you had the issue of planning, operational and planning models, guess what? In a planning model, what you're actually doing is you are going to run a host of simulations for different types of configurations, different types of outages. And what you're essentially doing is you may utilize a faster power flow option. And of those, you have the decouple, the fast decouple, and the DC. And guess what? They all build on the Jacobian matrix. They build on the Jacobian matrix, which is identifying the small changes between real power and angle, real power and voltage, reactive power and angle, and reactive power and voltage. And how does it do that? Well, guess what? Given that I have this big matrix, what we can do is find the interdependencies that are very strong and those that are very weak. And if you identify that they are weak interdependencies, therefore you can make certain assumptions, and those assumptions will allow the size of that problem, the size of the computation, to be reduced, because you've made those assumptions without significantly compromising your accuracy. So the decoupled power flow inverts two smaller matrices. It actually identifies that the relationship between power and voltage and reactive power and angle are very weak. So we assume those to be zero. And instead what you do is you invert two smaller matrices rather than invert a big matrix, which is the entire Jacobian. So you have managed to not only decouple, but separate those components. What do you do if you want to make it even faster? Guess what? You can take those two smaller matrices, but you invert them only once. So what you do again is you reduce the computational time, and moving forward, you are actually going to get to a point where you can get convergence, but you are moving so in a faster manner. And then, of course, there's one more. There's the DC power flow. And the DC power flow is very well suited to security analysis, and particularly when you want to look at planning. Why? Guess what? It's the fastest. It's the fastest because it requires a single iteration and a single matrix inversion, leveraging on the the power and the angle relationship that has been highlighted. And it's also referred to as the DC power flow because we are only looking at real power. We make certain assumptions in there, and we make the assumption, particularly the last one here, is that we are only going to calculate bus angles only, not bus magnitudes, because we assume that all buses are the same voltage. So what it does, it gives us a measure of where that power is going to flow from one point in the circuit to another. So before I step into power system security, which is building upon DC, Sharian, do we have any questions? Sharian, not hearing you.
Okay, sorry about that. We don't have any questions that have come in yet, so we can move forward. We should have a few in the next segment.
Sure, no problem. So when we're talking about power system security, and this is a term that we hear often, it is really about the ability and the practices designed to keep the system operating when components fail. And guess what? They do fail. They are going to fail. Whether they fail in a predictable fashion or an unpredictable fashion, the failure occurs and we need to be preparing for it. So when you look at the methods of power system security that, or I should say the standard that you will employ, it varies across region, it may vary across your regulator, but most importantly, the concept remains the same. You may have an N-M security. Normally, you may have an N-1 security, which identifies that for a power system to continue working satisfactorily, you must ensure that if one element is lost, the system will continue. And therefore, we say N-1. And perfect example is if you have a transmission line, the best way to ensure that you have N-1 is to double that. So you have 2 transmission lines. And that will vary, again, based on the measure of security that's needed for either a regulation perspective or within the context of the local geographic needs. It may vary, and it should be considered on a case by case. We talk about contingency analysis. Now I have a diagram, flow here, right, for contingency analysis. And the most important thing to identify is a contingency analysis is a series of simulations that you're going to perform based on a listing of credible outages. These disturbances are likely to happen, and what you want to do is to evaluate the performance on your network, and you want to do it, most importantly, before they arise, so you will have a better appreciation of how the system will respond. So therefore, we collectively refer to this as a defensive approach to power system operation. And guess what? The most appropriate model to use is the DC model. Why? Because it's very fast. It gives us the flexibility of having the potential to perform multiple simulations, get an idea if this solution can work or it cannot work. And if it can work, guess what we do? We go and do an analysis in full, and we may apply a AC power flow, which is the Newton-Raphson, the full power flow, so that we can get a measure of the real reactive voltage angle and voltage magnitude that is across the entire network and not limited to any one particular assumption. So contingency analysis, in a nutshell, allows us to address some of the uncertainty that we anticipate can happen. Placing too many outages on a short list for contingency analysis could be very time consuming. So you have to manage this very carefully, and what is often recommended is some sort of risk matrix that can identify which assets are more prone to an outage, and therefore if they are prone to an outage, you can treat with it accordingly. Preventative control actions and corrective control actions are critical. Why? Because they allow us to ensure that the power system is secure. Preventative is better than corrective, but costs more. Preventative means it happened, you are able to take steps before. And what I have here is this diagram that carefully illustrates this. And what it suggests is, if we have a power system that has a load of 1000 megawatts and we have generation of 1000 megawatts, supplied by 2 lines, you would ideally want these lines to be utilized and pushing as much power through it. However, these lines have a rating, and in these cases, the lines are rated at 500 megawatts. So therefore, the most economical way of generating power is not going to be the most economical way of transmitting the power. So what you will have to recognize is that if there's an outage and you lose one of those lines, you potentially will have a violation, which leads to the cascading story that you all heard before. We want to avoid that. So we make full circle and come back to recognize that if we can ensure that our generation dispatch will cater for an outage, while it may not be the most cost-effective solution, it gives us a measure of having a safe system that is secure. And that's the most important bit, is you keep the lights on. And therefore, having redundancy in your assets will be very instrumental to ensuring that you can achieve that. Other measures of preventative control actions would, apart from your line loading, will be useful to look at. And that goes back to having multiple assets, whether it's financially feasible, geographically feasible, or you may simply have some other challenges to address. The point is that there are corrective and preventative control actions that you should consider in order to make the system significantly more secure. Which leads us on to the transient analysis. Sherian, any questions there yet?
Yes, we have a question. This came in from William Hines from the Barbados Energy Division. Is there an international committee that meets and decides on the equations for new types of energy system technologies?
So thank you, William. Good to hear from you. So that really hinges, to answer to your question, is there's, to my knowledge, no global entity that will be able to influence any particular district authority on that. What you would potentially have will be some measure of guiding principles that, whether it be a standard association and institution, can make a recommendation for. But ultimately, those are usually set up by whichever regulating entities specific to the region, whether the mandates be just like in the USA, where we have the east side, the west side, and then you have Houston. You have those particular 3 bodies, the councils. Regionally, it may be dependent on the CARICOM initiative, it may be dependent on the government's policy. There's no set guiding criteria for that. Instead, it gives you the option to look at what is the most appropriate, what is the most feasible financially as well as technically to ensure that you achieve the targets. I hope that answers the question, William. Okay, so we will move on to transient analysis now. And when we talk about transient analysis, we go into the realm of power system stability. So let's define power system stability. So let me read this for you again. It's quite important that we get a firm grasp of this. It is the property of a power system which enables it to remain in a state of operating equilibrium under normal operating conditions and to regain an acceptable state of equilibrium after being subjected to a disturbance. Now, when we talk about operating equilibrium, all we are ensuring is that wherever we were, it does not have to be that place once again. However, once it is in a stable state, in other words, you have met the criteria where your generation matches your load plus your losses. Now, one acceptable state is a blackout. It's not a desirable one, but it is a valid state. So what we are going to discuss a little further now will be the steady state and the dynamic comparison. And let's touch on that. And if you look at this diagram that I have there with this little marble, what is interesting to note is that marble can potentially go on a roller coaster ride. However, if the marble is at one position and it's stable, it's in that equilibrium position, and it is dislodged, depending on how much energy or force it's dislodged by will dictate where it may rest eventually. But in order to determine where it may rest eventually, it will take a path to get there. So what you have here is a clear distinction between the change from one stable state to another state. The hope is that you get to another stable state, but the path to achieving that may not always be as stable as we think. So what you end up with is a transient as you move from one state to another state. And in order to get to that state, we are going to perform some measure of transient analysis. And that's what this slide is basically telling us, that the power system is constantly changing. And therefore we have many pseudo steady states. They all ought to be valid steady states that we can reside in, and we want to ensure that if there's a disturbance, we transition safely from one steady state to the next operating steady state. So what about transient stability in terms of a definition? Well, if we were to pull this back, what it really ensures is that we maintain synchronism. We want to ensure that our generators maintain synchronism when there's a severe transient disturbance. An example will be a three-phase fault. When you have a fault, how your system will respond is what you are going to investigate in that model. And the ability to move from that operating condition to another one without losing synchronism defines the process of transient stability, and that is defining our transient studies. And that is captured here in this state diagram. And note, partial blackout, partial fault or blackout is a valid state. It's an undesirable one, but based on the trajectory that you have when you move from one steady state to another, you may not get there. And a partial blackout may be an exit point in order to ensure that you do not damage your equipment further, and you can save some portions of the grid, meaning you can enter into a scenario where you may have some measure of electrical islanding. So some people may have, some people may not have energy and power. So when we talk about power system stability, this is an extract from one of the standards, and actually is a textbook as well, too, a very useful one. The Kundur, if any of you all outside there would like to look at it further. And it identifies that under the realm of power system stability, transient stability is just one type of study. We have other studies, which includes frequency stability, voltage stability, which is very critical when you have the introduction of renewable energies on the grid. And what you're looking for would be some measure of how you can ensure stability for frequency and voltage through those disturbances. Putting it into perspective, when we hear the term transient, we often wonder, well, where does this transient come from? Recall when we were discussing earlier about the synchronous machine. Well, guess what? The synchronous machine is a large mass, a large rotating mass. You have mechanical energy from a prime mover turning this prime mover and then creating electrical energy out of a generator. You have a transition from mechanical energy to electrical energy, and this conversion is going to ensure that you are on a path to have some measure of a runaway if you do not understand how you can control it. Your time constants are critical. Where do we get these time constants from? These time constants come from your generators. They come from the models, the excitation models that we look at. We also have some measure of correlation for each machine between performance and what the original time constants were. So why is this important? Well, guess what? When we look at your protection, if there's a fault happens and you want to ensure that, can your system regain its synchronism, or perhaps can it, I should say, should it not lose its synchronism? That fault needs to be cleared, and it needs to be cleared within a particular time frame based on the energy that will be stored during the fault. Because when you have a fault, essentially what you have just done is you have disconnected your electrical load. And by disconnecting your electrical load, your mechanical energy is being pumped into the system through this generator that will cause a change in your rotor angle. And what we need to understand is that the accuracy of these graphs that we look at really hinges on not only the accuracy of the model for building the network, but also the accuracy for the parameters that you have on your generator. When we talk about renewable energy generation, This becomes critical for us. Why? Because renewable energy is non-dispatchable. Also, these generators employ a lot of power electronic converters. They do not have the system inertia that a traditional generator will have, and therefore we can influence our grid stability quite easily if we are not conscious about how we look at our penetration. And our penetration based on, from a small share of RE to exclusive use of RE requires different levels of system studies. And guess what? What is always needed is a measure of your protection, your load flows, your short circuit analysis. You should be looking at your transient stability, and that only becomes more critical as you begin to increase your renewable energy penetration. And I cannot underscore how important it is to have a very firm appreciation, particularly when you're bringing batteries onto the system, the role that the batteries will play, the need for voltage ride-through capabilities, the need for frequency ride-through capabilities, the need to appreciate that when you have a battery on your system, how can batteries actually help improve your performance? Because what you now have is potential for energy and power, which, depending on when you have a fault, you may need more power to ensure that you can supply this demand for a short period of time, which is a significantly different type of energy need, because your rate of response must be very, very fast. And therefore, your customers must not see this outage. And this is against the backdrop that you do not have inertia on your system. So when you think about this, a generator, the control system that your generators would normally have will give you some measure of inertia. You do not have that flexibility with the power electronic system. So therefore, you must have a very fast responding system, and your controls must ensure that you can respond faster than the mechanical actions of the traditional system. And then, of course, that need for that technology, coupled with the drive to want to move towards a green state of energy production, means that we must look at the finances for it. So on this penultimate slide, initially we started to look at this block diagram, which would be what we have here in blue, and we looked at each one of these blocks. What we have managed to do is populate some measure of points against each one, and I just want to go over it to make sure that we can close the loop on it. And we looked at the contextual knowledge. We need to understand what's happening on your system. We need to look at the generation load profiles, the expansion plans. Does this actually fit, this model fit where we are now and where we want to go? Does this model actually have accurate and complete data? Is the data available? Are we using legacy equipment? Legacy equipment can often be more challenging to extract data. However, how frequently are we going to extract this data? And are we actually doing it correctly? Remember, it's only as good, what you get out is only as good as what you put in. And then, of course, we have some limitations. Limitations from a power system security. We may have operational challenges with the units themselves, the assets themselves, and we may have regulatory limitations. Software, whichever software you choose to use, you are always going to have an issue with compatibility between software modules, particularly if they're from different vendors. And that often means familiarity with moving from one software to another software, file type variations, something that you need to keep in mind, because it can often limit you in that perspective. And therefore, as you go deeper and deeper into your model development, you may find that the software may or may not give you the flexibility that you need at that point in time. And then, of course, the tools and techniques that we looked at, very basic. We introduced those tools and techniques to you all, the power flow, the fault analysis. We touched a little bit on the transient, but all in all, as long as you can interpret these results, that puts you in a good position. However, your validity of that interpretation really depends on the accuracy of the data that you use to produce the model. So Sherian, I'm going to stop here, and I would like to thank everyone for allowing me the time, and thank you all as well. Let's invite the questions. Sherian?
All right, thanks, Sanjay. So we have 3 questions for you.
Sure.
First one, how do you look at time varying events? Presentation seems to be focusing a lot on at an instant in time, but we know generation, production, and load consumption changes with time. So how do we look at the time varying events?
So this depends on the time of scale that you're looking at, right? So you have very short times and you have very long times. And in any simulation, and I'm sure our next presenter will probably be able to help a little more, shed some light into the flexibility that particular software can offer for that. Some software may look at the transient side, some may look at the steady state, and perhaps a longer steady state for a planning perspective. So I think without getting too much into the next presentation, I would say let's hear what the other presenter has to say on that, but it is very much dependent on the software used and how you intend to utilize the functionality of the software.
Okay, all right, thanks. So we look forward to getting some more information on that. What is your advice on making adjustments for environmental factors for which there is not a lot of data available in some of the Caribbean countries, for example, lightning?
So when you look at lightning, it depends on the type of study that you want to perform there, and that is going to be in terms of insulation coordination and insulation protection. The data that we have, we can utilize the next best, the next most compatible lightning data source, which would probably be dependent on your coronic level, and we would use the global map for that, because you have an opportunity to identify what is similar and then how you can apply that to the local context. But if it is you are going to utilize that on an insulation coordination exercise, that is totally different to a steady state approach for power flow, right? If you want to look at a fault analysis, what you simply have to do there is you can simulate the impact of what will be a lightning stroke, because it will essentially lead to a type of fault. So you simulate the fault at that point in the circuit, and it gives you a measure of the response of the circuit.
Okay, thanks, Sanjay. Final one for you, and I'm going to ask Prof. Sharma. We had two questions that came in for you, so just ask you to stand by after I ask Sanjay this question. Just to repeat, Sanjay, the textbook that you were recommending by, I think it's Kunder?
Power Stability Systems and Control by Prabhat Kundu.
Okay, so Power System, Stability, and Control. All right, thank you so much.
All right.
All right, and we have a couple of questions that had come in for Prof. Sharma. I think we have another minute. We could just take those two questions, Prof.
Sure.
Yes, I'm here.
All right. So the first one,
Just
practically.
before you go on to that, Sherry, just
Yes,
one of the, I just want to add something in terms of the time varying loads. And one of the areas you have to look at is your governor control and your governor time response. And many times you would find your governor control response time is actually faster than many of those time varying things. And those that the governor actually will take care of most of those. So that's when you have to become very intimately knowledgeable in terms of what your governor can do and what your load variation is like.
Okay, thank you for that, Prof. All right, so the first question, practically, are loads typically modeled as constant power, constant current, or constant impedance, or something else, and why? And when should each be used?
Well, it depends on the area that you're looking for, what you're really looking for in terms of your system. If you're just looking to look at power flow on your system, then you probably look at a constant power system, right? In terms of what is happening. If you're looking at to see what your voltage profiles would be on your system, you probably would want to look at voltage or current, but it depends on the loading that you're looking at. You can look at them at different ways and they give you similar answers, but it depends on which one is easier to represent in terms of the load model. You could have a varying voltage and a varying current, but they end up to be a constant load. Right?
Okay.
So you have to know exactly what is happening outside there.
Okay, all right. Thanks, Prof. And final question for you, at least for now. To calculate the line impedance with varying pole or tower structures, it may be impractical to model all of these varying impedances on the grid. What do you recommend as the best approach to address this?
Well, one would assume that most of your towers are aligned because this has to do with short or medium term line, right? One would assume that most of the structures that you have are of the same type. You would hardly find, except at the end or when you make an angle, that the structure changes. So you are going to use in terms of what are the majority of the tower structures that you have on the system and utilize that as the model. It's only when you actually go to angles that you change the structure of the line to compensate for the stresses and strains that are going to be at the corner for the tensioning that you're going to pull the conductor on. So you have a little change. But once you move from that particular pole or tower, it's the same thing again.
Okay, all right. Thank you so very much, Prof. Thank you, Sanjay.
Okay.
So now that we've gone into quite a in-depth introduction for grid modeling, we're now going to hand over to Leonard Holzman from Energy Nautics. Leonard is a renewable energy engineer there, and he has been involved in various power system studies looking at the impact of renewables on transmission, distribution, and microgrids. So most of his work has been conducted in Dixieland's Powerfactory, and so today he will give us an introduction to the usage of Powerfactory for such grid impact studies. And so I hand you over now to Leonard.
Thanks, Charian, for your introduction. I hope my screen is already live and you can see it all.
Yes, it is. You're good
Thanks
to
also.
go.
Yeah, thanks. Thanks also for my previous two speakers on this very nice introduction on power system analysis. So I'm going to talk on the specific tool of Powerfactory, Dixieland Powerfactory, that we are using a lot in our studies. So we are called Energy Nautics. We are a company from Germany, and we, as Professor Sharma already said, there are consultants who help with developing such models and doing studies, and we are like one of those consultants that actually do this, and we are also helping here with CCRI on one of the integrated resource planning studies with them and doing this with them. I'm just going to lose 2-3 words on our company. Like, we're doing studies all around the topics, especially with renewable energies, but also electromobility in both the developing as well as developed world. And here we're looking really at the broad range from distributions to transmission systems, and also looking at island and microgrids here. So we have just a very short overview on the countries that we have done investigations and studies in that you can see here, as well as some of our partners and that we have conducted the studies with. So as I said before, we have worked with Dixieland Powerfactory many years, and actually we have even collaborated with the Dixieland team on some of our studies, on our consultancy projects. We also have a workshop, an annual workshop on solar and wind integration that Dixieland is regularly supporting. And therefore, like, in these studies, we have like looked at very diverse systems, from really the smallest systems on islands, just a couple of not even 1 megawatt size, up to the broad scope of like whole interconnected systems, such as in Europe. And then also looking here from the study perspective, looking at like those calculations that we have seen in the previous presentations, where you would look at what happens in millisecond scale through RMS and EMT simulations, as well as what would happen in decades. Like, how do you need to plan your system in order to develop that? So for Powerfactory is, of course, only one tool of many tools that can do power system analysis. This is kind of the choice for our company to work this, but there are equally other software out there, of course, that can do basically the same. For Powerfactory, the main features that are listed here are, I'm not going to go through all the bullet points here, but of course, like all the previous things that the speakers have said regarding load flow analysis, short circuit analysis, then also the stability analysis functions that are all of course part of Powerfactory. And of course, what is essential for such a tool, for such a power system tool, is that you have a good representation of the network, that it's easy to handle your data, manage and manage it, and also like have a good visual representation of results and reporting, as well have like an easy integration with other programs in order to convert your data from one program to the other. These are essential features. And then Powerfactory on top of that has specific analysis tools for very specific analysis that you want to do. Of course, there are like these things such as contingency analysis, etc., that have been mentioned, but you will have also specific tools for the transmission network or for the distribution network. For example, to highlight a few here, for example, connection request assessments, where you would see where you could look at the impact of a new photovoltaic power plant on your distribution network and could quickly assess if it would create a problem on your network or not. And then there's more tools that are all listed here. You can also find, of course, these features on the website of Powerfactory if you really want to understand what exact features they have. To give you now a little bit of impressions from the more practical side, we have like looked now very in detail at the theoretical side, how power systems or power system models are developed, what are the equations behind it, and what considerations do you have to take. And here are just some results from how this looks actually in reality. This is, for example, this is an example from the Dominican Republic, where we had looked at the impact of photovoltaic power plants on the distribution network. So what you can see here, for example, on this network diagram is the modeling of a whole distribution network supplying a couple of thousand customers. This is the medium voltage network depicted. So this is like just giving you a visual impression how this can be looked at and handled. And we have, for example, used these networks in order to do studies about what will be the impact of that PV, of increasing PV penetration on those networks. So these are results and representations directly coming from Powerfactory. So you'll, if you do such analysis, you will get those figures. This is, for example, a voltage profile graph that shows the distribution feeder, and it basically looks at the voltage at the point of connection of the high voltage medium voltage transformer, and then this is the whole medium voltage network stretching up to 8 kilometers long, and then those colors represent the different phases. And so when you integrate on such a feeder renewable energy or distributed energy, such as the case with PV power plants, then you will have during peak load a declining voltage profile. So you will also usually have a high voltage set point at the high voltage medium voltage transformer, and then over time, if like during minimum load, this voltage profile will not decrease as much. And even if you have even some PV penetration, then what can happen is that you will actually have a reverse power flow from your PV penetration, which will increase your voltage. And so the Powerfactory here or any other power system analysis tools can really help you to understand what are the limits for PV penetration on such distribution grids, so they can really enhance your power planning abilities in order to accurately estimate what are the maximum penetration levels for PV, but also what measures could you take in order to increase this level even further, and what what will be the effectiveness of all these different measures, so you can really make informed decisions on this. Here is another example. This is from a German study that we have done in the last 2 years. And here, this is even more complex. We even looked not only on the medium voltage grid, but we looked also on the low voltage grid. And here, kind of we have here a very detailed network. Like this was a model with 25,000 nodes from the low voltage and medium voltage network, and even with this like a very large model, it is possible then to like you would also do those Newton-Raphson calculations, and while they are computationally extensive, still like the simulation of such a large network takes only less than 5 seconds to compute. So these can be really powerful tools and can really bring your power system planning much further. And in this case, in order to like have the integrity of the data ensured, we imported this data directly from the GIS, from the Geographic Information System of the distribution operator. So this is one of the tools or one of the possibilities that you can do here. So this basically shows we had to build a converter for this conversion from the GIS system to Powerfactory, but this can really give you a lot of applications for your analysis, for your power system planning, and you can especially like look at what will be the impact of future PV and electric mobility connections on your system, and you can also process with this grid connection applications, or look at the mitigation measures and optimization possibilities in terms of your voltage and power flow. So just to give you a couple of examples here. Of course, this it has been stressed many times by my previous speakers. You will really require very good data accuracy in general for such detailed power system models, and in this case, a very good data accuracy of your geographic information system. If we this was a couple of examples on the distribution network. Here are now some further examples on the transmission network. In general, what we have seen also from the previous speakers, we have talked about that we are looking at a specific instance of time, like a snapshot of the grid where we do our power flow simulations. And this can be, for example, a situation like the one indicated here. So this was also from a different study. And here you see for a future scenario of very high wind and solar power penetration levels, and here you see in green the wind power generation and the in yellow the solar power generation. So the overall penetration level of these inverter based generators is very high, so it's quite critical to look at such a situation. We have talked about this thing, like how could you look at many different points in time, and for that you would do a time series simulation. So you would basically do a snapshot for every, for example, 1 hour or every 15 minutes of time, where you could then do the power system simulation and look at this if there are any problems for any of these power of these load flows. So this can be done in also, of course, in Powerfactory. In Powerfactory, this is called a quasi-dynamic analysis. That's the term for it, or quasi-dynamic simulation, QDS. So if we look at such specific situations, so you will always have to think about, you can do this time series evaluation, or you just look at the most critical situations. So for example, for the integration of photovoltaic or in general renewable power plants, you should often look at the time when PV output is the highest. So you could investigate, for example, the PV output during peak and off-peak situations, and you can do this for a very simplified model. So this is an example from Bangladesh. And looking here at the situation of high PV penetration, and then you could look at specific supportive tools that also the PV can contribute. One of these things to always keep in mind is that such inverter-based generation can support your system with reactive power. With reactive power control, which can help your voltage regulation. And there are many studies and things to keep in mind. I will not, of course, be able to go into the details in this presentation here. Another example here is, for example, such thing called STATCOM capability, or also known Q at night, that PV plants could actually provide reactive power when they're when it is night. They still can provide reactive power and can be basically support the power system with these advanced features, and with the software, it's possible to actually quantify this benefit to the system and do your simulations about this. This was a very simple network here. This can, of course, get increasingly complex. This is another example from Ethiopia. This is really the full transmission network. And of course, here you see all the different lines and so on connected. And of course, it's good to have such a detailed representation of your network in order to really be sure about the results from your simulations. And also here, this was an example from a recent study where we then looked at the impact of new PV power plants, large-scale PV power plants in the order across 100 to 150 megawatt, looking at what will be the impact, and then we do these analysis with Dixel and Powerfactory here. The analysis that was also introduced by my previous speakers, such as load flow analysis, contingency analysis, short circuit analysis, and so on, and then also looking at dynamic stability analysis as well. And so also here on the transmission network, of course, the questions are a bit different from the distribution network. In the distribution network, you would often ask or answer questions such as like, how much PV penetration can I integrate into the network, or how much reinforcement will I need to do with future load growth or even electric mobility growth. And then, but however, on the transmission side, you will answer questions such as also, will there be voltage problems or overloading? But then also, will your protection equipment be impacted from changing short circuits, especially with regard to renewable energy and distributed generation? And then also, will your dynamic stability be maintained? And you will have specific dynamic models in your to do your RMS and EMT simulations that you will really have to take care of that these are accurate. And this was also mentioned by Sanji before, that this is a very so that the steady state analysis is something that you can really achieve, I would say, relatively easily in any such power system analysis model, and can set up your model here. But if it comes to those dynamic stabilities, you really need to know what you're doing, and it becomes much more complex because you need to set up those models or you need to know which I mean, Powerfactory has some set models that you can use here, but you may often have to parameterize these and know what you have to do. And then a lot of times also these studies will inform you how your generators will could contribute to the system, and that also includes any renewable power plants. They are new to the system basically for many countries, but they can actually support the system in terms of voltage and frequency control, and with this tool you can actually investigate this. So here are some just examples, visual examples also from the software on different dynamic stability analysis that we had performed. You could, for example, look at the thing like frequency stability, checking if you after certain contingency, maybe a generator is dropping out, if your frequency remains stable, and if your primary response and primary reserves actually are able to contain the frequency to an acceptable level. You could look at rotor angle stability if any generators would lose angle stability, voltage stability, looking at what would happen during a short circuit on one of your transmission lines. And also one of the things that was mentioned before was, for example, the capability of low voltage write-through, LVRT, which is also these simulations can really show you the added benefit from that, or because they would potentially show you that your system does not return to a stable voltage value after your disturbance, but instead you may end up in a blackout. And then last thing, rotor angle stability, we have also seen, I think it was one of the last slides by my previous speaker, where basically this needs to be remain stable and not go out of this graph basically. So just to wrap up this short introduction on the excellent Powerfactory, as I said, it is of course only one of many tools for performing power system analysis. Sorry, this is going directly to the next slide. But it is very capable of doing this. It is really an essential tool for distribution and transmission planning. And of course, what is essential really is that your data accuracy is very good with this. Sorry that it's always jumps back and forth. And that you also manage your integration with other systems, such as your geographic information system. And such power system analysis tools really become more essential with renewable power systems with higher renewable power shares, since the complexity increases. You will have much more different system states. You may have high PV penetration, high wind power penetration, high PV and wind power penetration, or you may have different geographical distribution of this infeed of power. So this can really help you in analyzing these different situations. And what we have seen also already before, you would investigate this on the one hand through steady state analysis, which comprises load flow analysis, short circuit analysis, then protection investigations, contingency analysis, and then also this question about like looking at multiple snapshots, so a time series analysis. And then on the other hand, also more like dynamic and transient analysis, such as RMS and EMT. And Powerfactory is really a very capable tool here, which offers really tools that are designed to help you make more like quick investigations and automated investigations by having really targeted tools here. So this you have already seen that this was my last slide, so thank you for your attention, and I'm happy to answer any questions about this.
All right, thank you so much, Leonard. We have one question so far. In your experience doing these studies around the world, do unregistered distributed generation, for example, rooftop solar, ever present problems for doing analyses?
So if I understand the question correctly, so of course, like distributed photovoltaic power will have an impact on your distribution grid operation. So this really changes the paradigm of always continuously having this flow of power from the upstream network to the downstream network. It changes that you will also have reverse power flows, and that creates the problem that you may have more complex voltage operation in distribution networks, and it can even lead to overloading of any of your distribution assets if the penetration is really high and it can also interfere with your protection system in the distribution grid. So doing these studies is really an essential tool in order to determine if you will get any problems or not. So when you have a new grid connection request in your distribution grid, often distribution system operators will do a quick analysis in order to see if this will create any problems or not. Or they may, on the other hand, just make it's called a hosting capacity and analysis, basically looking at least what is the maximum amount of distributed generation that you can add to a specific distribution network, so you can at least know until which level you can increase this before you maybe need to investigate it further or do any mitigation measures. I hope that clarifies your question.
It does, thank you. And I think this is going to be the final question because we're just about out of time. How is the utility to manage for multiple small systems on the network, unlike large-scale utility plants, which are acting as IPPs?
I mean, if you have multiple small-scale systems, you will have multiple power system models, of course, a separate one for each of your systems. You can integrate them in basically one model if you want to, but you could also have just separate models for each of them, and having them kind of separated and not all in the same view, basically. But this is just kind of like your choice how to handle best your data. But since they are not completely separated, it will also not create any issues if you just also have them in separate models.
Okay, thank you so very much, Leonard. We appreciate all our presenters that we've had this morning. And I think we've had a very meaningful introduction to grid modeling. And we look forward to the follow-ups that we will have for the countries that are currently doing grid modeling with us in the IRRP process. We will be beginning some hands-on training with them, and so you can look out for that. If you are already a part of the sessions that are coming up, then we are going to ask that you remain with us for a few more minutes so we can give you some information for those upcoming sessions. And for those who are not yet registered for one of the advanced training sessions and you're interested, we ask that you send us an email at resilience@cicri.org so that we can contact you when the